Okay. Good morning, students. In the last class, I have started the fifth module. I have started the first chapter in the fifth module. In the fifth module, we are going to study about integration and component-based software testing and the levels of testing and integrations testing. So for that, you have to study four chapters. First two chapters from the textbook 2 and other two chapters from textbook 1. I have started with the chapter 21 of textbook 2, that is integration and component-based testing. So in the last class, I explained what is integration and component-based testing, overview of that. Then I explained the different integration testing strategies. And today I'm going to discuss about testing components and assemblies. If I'll complete that, the chapter will be completed. And afterwards, I'll start with system acceptance and regression testing chapter. That is chapter number 22 of textbook 2. Okay. As I said, I have started with the overview of the integration and component based testing, because here we have the V model, and that is divided into four levels of granularity: module, integration, system, and acceptance test. So we have four different types of testing techniques, that is module testing, integration testing, system testing, and acceptance testing. And I explained what is model testing, integration testing, system testing, and acceptance testing. So model test checks the model behavior against the specifications or expectations, whereas the integration checks the module compatibility, that is, it checks the compatibility between the different modules. Next, system and acceptance test checks the behavior of the whole system with respect to the specifications and user needs. So once the specification is given and user needs are collected, according to that, the system is designed and developed, right? So hence, in the system and acceptance testing, we are checking the behavior of the developed system or the whole system with respect to the given specifications or user needs. And here we are concentrating on the integration test, because it is built on the foundation of thorough module testing and inspection, whereas the module test maximizes the controllability and observability of an individual unit. And the integration testing, it is acting as the process check on model testing. So I am repeating this is because in the previous class, very few people have connected, and that's why I'm repeating it once again. And the example for this is given. It's in 2004, a buffer flow overflow vulnerability is a single widely used library for reading the portable network graphics files, and this caused the security vulnerabilities in different operating systems such as Windows, Linux, and Mac operating systems, web browsers, and email clients. Okay, next I explained the different integration faults and examples for integration faults. So here we have six different integration faults. One is the inconsistent interpretation of parameters or values, and next one is the violations of value domains or or of the capacity or size limits, implicit assumptions on ranges of values or sizes. Next one is the side effects on the parameters or the resources, missing or misunderstood functionality, and the specification of functionality may lead to incorrect assumptions about expected results. And next one is the non-functional problems. Last one is the dynamic mismatches. Here, because many languages and the frameworks allow for dynamic binding, so that the problems will be caused by failures in mismatching when modules are integrated. Means when different modules are integrated, then in the dynamic binding, the mismatching problem arises. So these different types of faults I explained in the last class in detail. Here I'm just briefing it. So here we have six different types of integration faults and the corresponding examples for each fault. Next, I explained about the integration problems, where those integration problems may occur at different levels. Different levels means, as we know that in the software development process, we have series of steps starting from the requirement collection or the requirement specification, design, and development, and there is a chance that the errors may occur at these different levels. And these are nothing but the integration problems. Integration problems means when we are integrating or combining the different modules together, then the problem arises. Such type of problems are said to be integration problems. So integration problem. Here we have see here some classes of integration problems can be reduced or eliminated by using the proper design methods or proper designing techniques and good programming environment. So different problems can be reduced or eliminated. One such example is in the applications which is demanding management of complex shared structures, choosing a language with automatic storage management and garbage collection. It reduces memory disposal errors such as dangling pointers and redundant deallocations. So this is one example. Here we can reduce the integration problems. And here one more is with the mismatch, right? So in C or C++, we require to use the safe alternatives of unchecked procedures, such as requiring for a string copy and a string CPY, that is a string length CPY in place of string copy. So here in place of string copy, if we are using strlcpy or strncpy, then we have to check the safeness of using that particular function. So checking of this particular function is much easier than checking for its safe use, because when we say that whether it is safely usable or not, only when the program is executed, right? Until that, it is very difficult to check whether that is safe, use of that function is safe or not. Hence, instead of checking for the safeness, it can just check for the presence of this particular function. Okay, like that we can avoid the different integration faults. And next, we have studied about the integration testing strategies. So this also explained in the last class, because here we are performing the integration testing in an incremental manner. Why we are going for incremental manner? Because the software system development of a software is also a incremental process. Incremental process means we'll starting from the basic thing, means we'll start from the collection of the requirements, design, development, integration, etc. And that is the incremental approach, software development. And similarly, we are applying the testing the strategies in the incremental approach. So why we are using the incremental approach? Because we have to detect the faults or the errors at each stage of the software development, right? And we want to are we aimed at detecting the faults or the errors as early as possible. So if we detect the errors as early as possible, then those errors can be corrected with the minimum cost, right? And when we are going for the complex interactions, so then these complex instructions may hide the faults or the failures that are manifested and may propagate across many modules. And may propagate means they can pass through different modules if such errors are undetected in different modules, and if the errors are detected only during the operation of that particular product, then correction of such faults is very very costly. So we have to avoid such things. And whenever we are performing the assembly of the modules, and these are our assembly of modules are incomplete without the construction of the scaffolding. So you know that different scaffolding techniques, that are driver steps or various kinds of instrumentation. So here scaffolding means what? Here it is, scaffolding is nothing but an additional code we are using to perform the testing and to detect the faults. So we are using the additional code in terms of driver steps or other kinds of instrumentation. Okay. And but when we're using the scaffolding in the form of driver steps or the various kinds of instrumentations, what happens? The cost may increase. So in order to avoid the cost, so what we can do is we'll wait until all the modules are integrated, and then finally we can test the system at last. But that approach is called as the Big Bang approach. So in the Big Bang approach, what we are doing, we are not checking or we are not testing each module in turn. We'll wait until all the modules are integrated. Once all modules are integrated, then we are testing them together, and we'll check whether any faults are there or not. And that approach is called as a Big Bang approach. So in the Big Bang approach, neither the steps or the drivers need to be constructed or can be developed, because we are not mainly dealing with either the steps or the drives. So we are mainly dealing with the operation of all the models which are integrated together, and we would like to know whether when once all the modules are integrated, whether they are all operating in a correct manner or not. So only we are dealing with that. But if that is the case, what happens here? We are saving the cost, right? We are not investing on the scaffolding techniques, such as we are not including the steps or the drivers. So we are not concentrating on that. So obviously the cost will be minimum, or we will develop that by using lesser cost. But these savings are more than offset by losses in observability, diagnosability, and feedback. Why? Because since we are not observing each module at each stage of development. So in the Big Bang approach, as I said, we are integrating all the modules together. Finally, we are testing. If something happens to any module, then that leads to the failure of the entire system. Right. So, and it is very difficult to check in which module the errors has occurred. Right. There, the observability is reduced. So, once the observability is reduced, then diagnosing the errors in the different models is also difficult. Hence, these savings are more than offset by losses in observability, diagnosability, and the feedback. Right. So feedback means if the system works fine, then we will get good feedback from the users or the customers. If the system is not working properly, obviously the customers will give the bad feedback, right? So yes, this affects once again the system, right? Hence in the we need to test the module at each stage of development instead of waiting till last. So we can't use the Big Bang approach in all software development process. Because here, delaying integration testing hides the faults whose effects do not always propagate outward to visible failures. And requiring the whole system to be available before integration does not allow early test and the feedback. So faults are detected at the end stage, and they are very costly to repair. And when compared to other approaches, Big Bang integration testing or Big Bang approach is less rational strategy than an attempt to recover from a lack of planning. So, hence, the Big Bang approach is also called as a desperate tester strategy. So, the example for this, I explained the memory leaks in the last class itself. And next, we'll move on to the testing components and assemblies. Before that, this also explained. So before moving on to the assembly of the systems, so first we'll see the incremental testing, partially assembled systems. Here we have the two main classes for assembling the systems. One is the structural method, and the other one is the future oriented method. We'll see the difference between the structure oriented method and future oriented method. So in a structural approach, what happens? We are constructing the modules first, and then we are assembling the models, and then assembled models are tested together in an order of in an order based on the hierarchical structure. So here we'll use the hierarchical structure in order to construct, assemble, and test the modules. Okay, so hierarchical structure means it is tree structures one by one. Okay, so what we will do first, we will construct the modules. Next we will assemble the modules. Then once the modules are assembled, or once the modules are integrated, then we are testing those modules. Hello. I'm having class. You call me afterwards. Okay. Next one is so we are talking about the structural approach, right? So structural approach also includes the bottom up or the top down, and also the combination of these two. And the combination of these two is called as a sandwiched approach or the backbone approach. Understood? So structural approaches includes the top down approach or the bottom up approach, and also the combination. Sometimes we'll also use the combination of these two, and that is called as a sandwiched approach or the backbone approach. Okay, so this is about the structural approach. And next, in the future oriented approaches, these derive the order of integration from characteristics of the application and includes the threads and critical modules strategies. Okay, so feature oriented approach includes the characteristics of the applications, and it also includes the threads and critical module strategies for system testing or for incremental testing. So, as I said, the structural approach includes the top down and the bottom up approach, and these top down and bottom up strategies are the classic alternatives in the system construction and incremental integration testing. Because as the models accumulate, we need to identify the different faults, and we need to check whether all the models are working in a correct manner or not. So the last topic of this chapter is testing components and assemblies. So as we know that how the software products are constructed, or how the software systems are constructed, the software systems are constructed either part by part or whole, means the entire product can be constructed. Okay, so how it is constructed? By using the pre-built software components. Okay, we'll use the pre-built software components, and we'll assemble those components, and we'll construct the software product in a partly manner or in the whole manner. Then a key characteristic of software component is that the organization that develops a component is distinct from the several groups of developers who use it to construct the system. See here, different organizations may use different methods, and they may use different software components to construct the product. That's the case. A key characteristic of software component is that the organization that develops a component is distinct from several groups of developers who use it to construct the systems. So it is different because group of developers are available. Each can use it, their own method to construct or to develop the components. And when we are combining components together in order to form the software product, and that may be used in distinct way or in different way from different users. Okay. The component developers cannot completely anticipate the uses to which a component will be put, because the component here, the users are different, the designers are different, the developers are different, means implement. One team is looking into the implementation, one team is looking into the system design, other team is looking into the system requirement collection, right? So each team is different one, right? When they are performing their task is either requirement collection or designing or the development, because each different team is involved in each different task, and they cannot anticipate the uses of that particular component. Okay, suppose let us consider that one module I have developed. Okay, and I am not completely know about where actually the users or which users are using it or for what purpose they are using it. The developer doesn't have the any idea about it. Okay, the developers are having the limited knowledge about that component. They have the knowledge about how the module is developed or how that particular component is developed. They doesn't have the idea about how that component is going to be integrated into the system, or how it is used, or how it is used by different customers or the users. Okay, because the developers are mainly concentrating on developing the system. or developing the module or developing the component. They doesn't have the idea about in which product it is going to be integrated, or in which product it is going to be placed, or which is used by other users or by any customers. The developers doesn't have the idea about it. So hence the component developers cannot completely anticipate the users to which the component will be put, and the system developers are having the limited knowledge of the component. So they are having only the knowledge about how that particular component is designed and implemented. Okay. Testing components by the component developers and assemblies by system developers therefore brings some challenges and constraints that differ from testing other kinds of modules. Why? Because as I said, different teams are involved in designing and assembling or implementing it. So bringing all the different components is a major challenge, and also there is a constraints when we are integrating or combining the different modules together. What happens? Some modules may work, some modules may not work. Then the whole system fails. If any one of the module in the system is not working, then what happens? The entire system fails. So these are the challenges we need to face when we are integrating the different modules to construct the entire system. And here, the advantage is here we can make use of the different components, or we can reuse the components again and again. But the major disadvantage is the advantage of component reuse for quality are not automatic one. Okay, because we need to do that, and they do not apply to the code that was developed for a single application and then scavenged for use in another. Okay, the advantage is we can reuse it, but they are not automatical, means we cannot automatically reuse the components, but manually we need to do that. Okay, and the other one is they do not apply to code that was developed for a single application and then scavenged for use in another, means for the components are not developed only for the particular code. Okay, so they have developed for a scenario. They consider the scenario. For that scenario, they have developed the components. So that same components can be used in the similar scenarios with a very minimum modification. And above two advantages, that is these two advantages, component reusability and they're developing the what the components for the scenario, not for the particular code. These are the two advantages, and these advantages are balanced against two considerable disadvantages. So one disadvantage is a component designed for wide reuse will usually be much more complex than a module designed for a single use. Okay, because this is the component, and we when we are designing the component, we'll keep in mind that that component can be reused widely. So then as since we are using the components for different scenarios or applications, obviously the complexity of that component increases, and this complexity is more when we compare with the the component which is developed for a single use. So when we develop the module or the component for a single use, then that is simpler when compared with the components which are designed for reusability. Obviously, the complexity increases there, but here the complexity means the module is simple one, or it is not much complex when the module is designed for a single use. A rule of thumb is that the development effort. So here we will include the analysis as well as the testing as the development of effort. Why? Because once the systems, requirements are collected, those requirements are analyzed, then designed, and finally implemented. And at last, we are performing the testing, right? So each thing is included. Development includes the analysis as well as the testing. It's a widely usable component, and it's at least twice that for a module that provides equivalent functionality for a single application. So if the component is a reusable one, and we developed that component by definition and without considering the full knowledge of the environment. Okay, so we have developed a particular component according to the requirements given, but without considering where actually that particular component is going to be placed or going to be operated, means we are not considering the environment. Okay, then if that is the case, what happens, it is exceptionally difficult to fully and clearly describe all the assumptions, dependencies and limitations that might impinge upon its use in a particular application. So it's very difficult to integrate that component or place that component so that it can clearly operate and it gives the correct output. So it's a very difficult task to clearly describe all the assumptions, dependencies, and limitations that might impinge upon its use in a particular application. So hence, developing a component for a single use or developing a module for a single use is more easier, and that particular module is very simple when compared to developing the modules or the components for reusability, because those components when they are developed without the knowledge of the environment where actually that is going to be placed, right, and hence the complexity increases. Hence, once again, depends on the requirement. Either we can use the components again and again, or that can be designed for the a single user. So this is about testing components and assemblies. This completes the chapter. That is the integration and component based testing. That is the chapter number 21 of module 5. So that is the first a chapter of module 5. In the next class, I am going to start the new chapter, that is chapter 22nd, and that is the second chapter for in module 5. Okay, so that chapter is called a system acceptance and regression testing. That will start in the tomorrow's class. And today I completed one chapter, right? So that is in integration and component based testing. If you have any doubt, you can ask now. Yes, any doubt? Sachin, Misbah, and Suraj.
No, ma'am.
Any doubt?
No, ma'am.
Hmm? If you have no doubt, I'll end the class. So this is the first chapter of